All right, so when we're looking at these permutation problems where we're looking at a circle, we want to keep in mind our knowledge that, okay, if I want to find an arrangement for n objects in a circle, I have to take n minus 1 all factorial. But like with a lot of questions, we can extend this further. We can start applying some restrictions here. So we've got 4 men and 4 women at a circular table, and men and women need to sit in separate groups. And we want to go beyond just having this knowledge of this formulaic approach. And I really like to draw pictures to approach something like this, right? So I've got my table, straight over here. Got my table there. I've got my 4 men sitting on maybe one side, and then 4 women sitting on another because they're in separate groups, right? We know from before with restrictions that in order to treat them in separate groups, it's much easier to think about them as a single object like this. Right? But with a circle, we want to think, okay, how many objects do I have? Well, I have 2 objects there. That would actually just be 1 factorial ways we can arrange that, because if you rotate these around, it doesn't actually change the arrangement. But within these groups, I can actually change them, right? How many ways can I assign 4 men to 4 seats in that particular group? Well, there's 4 of them there, so that would be 4 factorial. And same for the women, there's 4 of them there for 4 seats, so that would also be 4 factorial. Okay, that's part A. What about part B? What if they're alternating? Now, if they're alternating, it becomes a bit trickier. And this is why we want to have a good understanding of permutations in a circle. Because one way that we can approach it is that we can think about, all right, how many people can I allocate to each spot? So if I draw my circle again, now rather than drawing men and women, if I think about how many people can I put to each seat, and because there's 4 men and 4 women, it doesn't really matter which one I put first. Let's just say I put 1 man down first. Now, how many ways can we do that? And remember, because of the nature of a circle, the first person you put down, there's essentially only one way to do that, because it doesn't matter where they're sitting, right? There isn't anything fixed yet. There's really only one way to put that first person down. So let's say I'm putting down all the men. There's one way to put 1 guy down, and I've got 3 men left. So I've got 3, then 2, then 1. Now, the women and men have to be alternating, so the women have to go in between there. Now that the people are fixed in, when I put the women down, I do have 4 choices because people are fixed in. And then how many women are left? Well, then there's 3, there's 2, and there's 1. And you have this nice little pattern here. You'll notice that if you just take every second number, well, that gives me 4 factorial. And then over here again, that gives me 3 factorial. So that's 4 factorial times 3 factorial. And that's how you get that answer there. So we want to be comfortable with drawing our positions and grouping them together, but we also want to be comfortable with this notation where I'm writing how many choices do I have for each seat. Same thing with something like this, right? They always come up with some creative things. So 3 Tasmanians, 3 New Zealanders, and 3 New South Whalers. Don't know what you call someone from New South Wales. They're randomly sat around a circular table, a round table. We want to know the probability that they're in separate groups. Okay, so 2 things I'm looking at when I see a question like this. First thing, I see probability. Okay, so I'm already thinking, all right, I need to always have for probability a sample space and the number of favorable outcomes. And I'm also seeing separate groups. Before I jump into the question, I'm just going to draw a picture. Right? I want this situation where they're in separate groups. So my Tasmanians are together. So there's 3 of them there. My New Zealanders are together. And my New South Whalers, let's use W for those, they're over here. They're in 3 separate groups. Okay. Before I kind of address that, let's go back to the probability. The sample space, right? How many possible ways can this occur if there's no restrictions? Well, if you think about it, you've got 9 people here, and I know that for n objects in a circle, it's just going to be 9 minus 1 factorial, or that's just 8 factorial, right? So, what about if they are in 3 separate groups? Right? How many ways can that happen? Well, again, like over here, I can treat them as a single group like this, right? So that gives me 3 groups there, and then essentially I'm doing this same problem again, and I've got 3 objects that I'm arranging in a circle. There'd be 1 less than that, so 2 factorial ways I could do that. So favorable outcomes, sorry, not favorable outcomes, I'll say separate groups. Okay, so that's going to be 2 factorial. But remember, all right, I'm not only just arranging these groups around the table, I can actually arrange them within themselves. How many ways can that happen? Well, you've got 3 New Zealanders there, so they can be arranged 3 factorial ways within that group. 3 New South Wales, and 3 Tasmanians. Right? And if you calculate that, that will give you the number of the number of ways you can have separate groups, which is, let's do that quickly. Okay. So now what's the probability? Because we actually need to answer the question. The question is saying, what's the probability that we'll be in separate groups? Well, to do that, I know I have to take the number of favorite outcomes, so 432, and divide that by the total number of possible things that can happen, so 8 factorial. And it's not too high, 3 over 280, or just over 1%, I think. So that's how you answer some questions about permutations in a circle.